today. Today we have Dr. Sorry, let me open up the page first. Okay. Today we have Dr. Ji-Yoon Lee from the Department of Civil and Environmental Engineering at Washington State University. She'll be talking to us about risk and resilient assessment of infrastructure systems. And Dr. Ji-Yoon Lee is an assistant professor in the Department of Civil and Environment Engineering at Washington State University. Prior to joining WSU in 2017, Dr. Lee served as a postdoctoral scholar at UCLA and visiting faculty at the University of Central Florida. She holds a PhD in civil engineering from Georgia Tech and an MS in civil engineering from Stanford University, and a Bachelor of Science in Architecture Engineering from Korea University, South Korea. Dr. Lee's research experience and interests lie in general field of risk-informed decision-making for civil infrastructure performance and integrity, with specific interests ranging from stochastic models of natural hazard to structural reliability and risk assessment optimization, human decision-making, and infrastructure community resiliency. She is a historian of ASCE 722 Load Combinations Subcommittee and a member of ASCE Infrastructure Resilience Division Task Group 2 and Task Group 3, which deals with risk assessment of structural infrastructure facilities and risk-based decision-making. Welcome, Dr. Lee, to the ESIC seminar today. We look forward to your presentation.
Yeah, thank you for inviting me to this seminar and for giving me this opportunity to talk about the risk and resilience assessment of infrastructure systems. So in today's presentation, I will start with the definition and the basic procedure for engineering risk and resilience assessment. And then we'll introduce a new approach to combining the multiple risk factors in assessing their impacts on larger scale infrastructure system. And finally, a supply chain system will be introduced as an example to show how this new approach can be applied at the system level. Okay, so a natural hazard is a natural phenomena that has a negative effect on human and the environment. So infrastructure systems are vulnerable to natural disasters, and the human and economic losses resulting from such disasters are significant. So for example, Hurricane Katrina of 2005 was the single most costly natural disasters in the United States history, resulting in about like 1,800 fatalities and around $125 billion in economic losses. And it destroyed 20,000 utility poles and affected more than 2 million homes and businesses. And then it took almost 6 months to fully restore the power system. And the wildfire is another type of natural disasters affecting the human and the environment significantly. So the Camp Fire was the deadliest and one of the most destructive wildfire in California history, resulting in 85 fatalities and destroying 14,000 residences. So it burned the area with the size of Chicago, and the total damage was estimated at $16.5 billion. So here, I'd like to share some interesting points found in the historical natural disaster. So the left table shows the natural disaster by the death toll, and most of these events occurred almost 100 years ago, which means that human losses from natural hazard have decreased significantly in the past century. However, the top 5 costliest natural disasters shown in the right table occurred more recently between 1994 and 2017, which means that the economic losses from the natural hazard have increased significantly in recent years. And similar observations were found around the world. So annual total damage has increased tenfold between the period between 1976 to 1985 and the period from 2005 to 2014 from $14 billion to the $140 billion. Then what are the main causes for this trend? So the possible answers to this question can be found in the next slide. So the human losses resulting from the natural hazard have decreased significantly over the last century due to the improvement in the building design standard and construction practices, improved disaster forecasting, and timely public warnings, all of which could be achieved through the advanced technology and improved understanding of hazard. However, economic losses have increased dramatically in the past decades and are expected to increase in the future due to the increasing risk, such as the population growth and urban development in hazard-prone areas, as well as the global climate change. And the importance of appropriate risk management and risk-informed decision-making for the disaster preparedness can also be found from the comparison between the 2010 Haiti earthquake and 2010 Chile earthquake. So the January 2010 earthquake in Haiti had a magnitude of 7.0 and caused 230,000 fatalities. And this earthquake destroyed Haiti's economy and infrastructure had been recovered very slowly. But by comparison, the magnitude of 2010 Chile earthquake was 8.8, which was the fifth largest earthquake in the world since 1900, releasing about 500 times greater energy as compared to the Haiti's earthquake. However, Chile's death toll was 550 fatality, which is 400 times less than the fatalities of the 2010 Haiti earthquake. Then how was it possible? It was because Chile had a better understanding of the earthquake risk, which resulted in better building codes and the earthquake-resistant construction before the earthquake event, and the strategic implementation of policies that address both the immediate recovery needs and long-term planning. As such, the risk assessment and management play a vital role in reducing human and economic losses, as well as the social disruptions from disasters. Okay, then before talking about the risk assessment, we first need to define risk. And risk is a combination of three components, including hazard, exposure, and vulnerability. And hazard is a potentially destructive physical phenomena, including the natural and man-made hazard, such as earthquake, hurricanes, tornadoes, flooding, wildfires, tsunami, volcano eruption, and even the intelligent attacks. And exposure is the elements at risk that could be affected by the hazard, including the people, buildings, infrastructure, and the environment. And the vulnerability is the likelihood that elements will be damaged when exposed to a hazard. So for example, a building with multiple stories will be more vulnerable to the ground shaking from earthquake than a one-story building. And another example is that an elderly person may be more vulnerable to the impacts of flooding because he or she has more difficult time in evacuating or moving quickly. Therefore, in order to assess risk, these three components should be defined first. So from an engineering viewpoint, the risk-informed decision-making has the four basic steps: risk identification, risk modeling, risk assessment, and risk management. So in the first stage, we can identify the three risk components, which are hazard, exposure, and vulnerability, as I mentioned in the previous slide. And then the second step is to develop or simulate the stochastic models of the identified risk components. So for example, let's suppose that we perform a risk assessment of a residential community located in Miami, Florida. And then the exposure will be the people, buildings, infrastructure, and some natural environments located in this community. And because the Miami is one of the most hurricane-prone areas in the United States, so hurricanes can be considered as a major natural hazard. And to model the hurricanes, we can generate a large number of the hurricanes from its initiation over the Atlantic Ocean to its final dissipation after making landfall. So we can record the number of hurricanes hitting the community per year, and then we can also record the intensity of each earthquake. So this is the procedure for generating the stochastic set of hurricanes. And then we also have to investigate the vulnerability of the buildings. And then we also have to just consider some vulnerability of the people and the natural environment. But during this presentation, I'm gonna just focus more on the physical aspect of the community. So here, the vulnerability of the buildings can be represented by the fragility curve. And then I'm going to talk about the fragility curve in more detail at the later of this presentation. But here, each building has different vulnerability due to its own dimension, like the floor plan, layout, construction material, and different structural behavior. Okay, then from the results of the hurricane simulation model, we can model the structural load. And then by performing the finite element analysis and the nonlinear dynamic structure analysis, we can also study the resistance or the building capacity. So this figure shows a joint probability density function of the structural load and the structural resistance. And then we can calculate the probability of building failure by computing the volume under this joint probability density function, which is less than this limit state function, which is the comparison between the structural resistance and structural load, because the building will fail when the structural load is greater than the structural resistance. So this equation just shows how to compute the probability of building failure from this joint probability density function. So this is the procedure for the risk assessment. And then the final step is the risk management. So we can just make some decision based on the risk assessment and other constraints for the purpose of mitigating risk and or improving the resilience of the community. And as many of you have already heard, resilience is a hot topic in many different disciplines. And the concept of resilience has received great attention in recent years due to the repeated natural hazard and their high consequences to humans and the built environment. So resilience can be broadly defined as the ability to prepare for and adapt to changing conditions and withstand and recover rapidly from disruption. And resilience capacity can be classified and categorized into these three parts. So first, absorptive capacity is the capacity of the system to absorb and resist the impact of perturbation and to minimize the negative impact of the disruption. And second, adaptive capacity is defined as the ability to successfully respond to future changes and conditions by adjusting to potential damages and just taking advantage of opportunities. And lastly, the restorative capacity is the ability of a system to be restored quickly and efficiently in the case if the absorptive and the adaptive capacities are not sufficient, and then the system cannot maintain on an acceptable level of the performance. Then how can we quantify the resilience of the system? So here in this figure, the horizontal axis indicates the time and the vertical axis indicates the functionality of the system. So the functionality of system can be just measured by many different types of the performance measure. So for example, if I consider the performance of the transportation system, then its performance can be measured by the traffic time between the origin and destination. And if I consider the performance of the water distribution system, and then I can measure its performance by using the number of the customers with the water services. And then if the disruptive event occurs at this point, and then the system will experience some sudden reduction in functionality, but will recover fully as the restoration process will be complete. So here, the reduction in performance is the loss of functionality, and then it may be determined by the absorptive capacity, and then the length of this recovery phase can reflect the restorative capacity of the system. And then the resilience can be measured by the area above this post-disaster recovery trajectory. So this part is the resilience loss. And then in order to improve the resilience of the system, we have to minimize this resilience loss. And in today's seminar, I'd like to introduce one of my recent studies on multi-component resilience assessment for a supply chain system to illustrate how risk and resilience assessment can be used at the system level. I should mention that although this new resilience assessment framework will be illustrated with a supply chain system, but the general framework I'm going to propose can be applied to other types of infrastructure system, such as electric power grid, water distribution system, transportation system, and so on. Okay, then what is supply chain system? So supply chain is a complex network system involving the whole process from the production of source material to the delivery of a completed product to the end users. So it also includes all the individuals, resources, technologies, organizations, and activities in this process. So here I'm going to focus more on the physical aspect of the supply chain system. So the supply chain system can be modeled as a graph consisting of different set of the node and the links. So as you can see from this figure, the supply chain has different types of the node, such as the raw material production node, some of the refinery, oil crusher, or the storages, and the final destination node, and the links between the supply chain node or the transportation routes in order to deliver the product from the raw material production node to the final destination node. And earthquake or other extreme natural hazard events may seem like rare events, but the geographic spread of the supply chains across a larger region increases the possibility of the system to be exposed to such hazard. Moreover, due to this geographic spread, each part of the supply chain may be experiencing different types of the risk factors. So let's suppose that the supply chain system is located in the Pacific Northwest region. And many different events can occur simultaneously. So for example, because the Seattle is located in a high earthquake area, so the supply chain system, especially this portion of the supply chain system, can be attacked by a magnitude 7.2 earthquake event, for example. And climate change may affect the frequency and severity of the drought inland, and some of the feedstock node in the supply chain system could be affected by the droughts. And at the same time, demand may increase due to the local market competition, and some of the facility may shut down due to unexpected events. So like this, a supply chain system can be affected by many different types of uncertain events and conditions due to its geographic spread. And it can be more clearly shown in the global supply chain system. And moreover, while a supply chain system is seldom designed with a specific service life in mind, its planning decision should consider a sufficiently long-term horizon to maintain the system functionality under various uncertain conditions. So for example, if we consider, say, the 20-year planning horizon, then a supply chain system is exposed to many different types of internal and external factors. So let's say that at the very beginning of the planning horizon, the supply chain system may be affected by some frequent drought. And at some point in time, huge hurricane will occur and destroy some major facility of the supply chain system. And maybe in the future, more connected and autonomous vehicle will be introduced in the general transportation setting and will improve the logistics in the supply chain system. So as you can see here, these two are some kind of the threats that may induce some negative effect on the supply chain performance, while this kind of the risk factor can bring about some opportunities, which means that it can cause some positive impact on the supply chain performance. Therefore, considering that a supply chain system is distributed over a large geographic region and should maintain its functionality over its planning horizon, we need to consider the impact of various uncertain events and conditions on the supply chain performance. Okay, so as introduced earlier, most existing resilience studies have focused on a single type of the natural hazard and developed the resilience enhancing strategies to minimize the negative consequences of the hazard event. So for example, here we consider only a single occurrence of a hazard event and we try to minimize the resilience loss. And moreover, it starts with a what-if scenario. So rather than considering the uncertainties in the time of occurrence of the hazard event, it just assumes that a hazard event occurs and then just to try to minimize this resilience loss. However, there might be some possibility that there will be multiple events over the planning horizon. So this study addresses the shortcomings found in the existing and conventional resilience assessment approaches by considering the multiple types of events and conditions that may occur during the planning horizon. So as shown in this figure, this study considers the whole planning horizon and quantifies the impact of each risk factor on the supply chain performance so that we can consider the absorptive, adaptive, and restorative capacities of the system. And by doing so, contrary to the conventional approach, this study not only mitigates some negative impacts, but also capitalizes on opportunities that some future events will bring about. Okay, so this slide shows the general procedure for this proposed approach. So this framework consists of two stages, multi-risk assessment and multi-component resilience assessment. So the first step is to identify the risk factors occurring at different points in time and space, model and simulate the individual risk factors, and combine them to evaluate the supply chain long-term performance. And in the second stage for a given scenario, as shown in this figure, the three resilience components are measured, and then I'm gonna talk about these three different resilience components later, and then combine to quantify the overall resilience index of a supply chain system. So I'll go into more detail about the step-by-step procedure. Okay, so the first step is to identify possible uncertain events and conditions that may affect the supply chain performance over the planning horizon and to classify them into the several categories. So this table is just an example, and in this specific example, we identified several risk factors and classified them into the 8 categories, including the natural and man-made hazard, climate change, market, supply, or the finance-related uncertain events, technology development, and human or the organizational behavior. And as mentioned earlier, some of these risk factors can be considered as threat, while others can be considered as opportunities based on their negative or positive impact on the supply chain performance. So for example, in this table, the advances in the conversion technology can be considered as an opportunity due to its positive impact on the supply chain performance. And because most of these events and conditions are problem and site specific, they should be identified based on the type and location of the supply chain of interest. In other words, if we consider the supply chain A, and then we have to just identify like the different risk factors that may be the most appropriate to this supply chain A. And then if you're gonna analyze the risk for the supply chain B, and then we have to just completely do this analysis specifically for the supply chain B, because it may be exposed to different types of the uncertain events and conditions over the planning horizon. Okay, then after identifying and categorizing the possible uncertain events and conditions in the future, then individual risk factors should be modeled and simulated over the planning horizon. So every factor has its own characteristics and should be modeled by using the appropriate risk assessment approaches. So for example, we can forecast the time of occurrence and intensity of an extreme events from the natural hazard based on their physical characteristics and probabilistic hazard analysis. And some of the uncertain events and conditions can be forecasted purely based on the historical database, or other factors involve uncertainty, and then it should primarily rely on the expert's opinion. So after realizing each type of events and conditions using appropriate method, the realizations of all events and conditions are layered together to generate a scenario over the planning horizon. So this is the procedure to generate only one of the many plausible future scenarios, and then this procedure should be repeated until a sufficiently large amount of the future scenario will be generated. Okay, then now we need to talk about how we can measure the supply chain performance. So in the conventional approach, either the unmet demand ratio or the total cost is a commonly used performance measure. However, in this study, we will use the three different supply chain performance measures, including unmet demand ratio, resilience cost function, and the reward function. And unmet demand ratio measures the ability of the system to meet the customer demands, and it can be quantified by this equation that is the sum of the unmet demands over all the demand nodes divided by the sum of the total demand. And the resilience cost has the four different components, including the unmet demand penalty, the restoration cost, and the changes in the transportation cost and the operation cost due to the risk factors. And the reward function is used to assign the reward for demand surplus to account for some system redundancy. So this term may not be an actual economic benefit that the system produces, but more like a benefit obtained by meeting the minimum target demand under any uncertain scenario in the form of the redundancy or backup. So as you can see here, all these performance measures are scenario dependent and time dependent. And because the performance changes over time due to uncertain events and conditions, so all of these performance measures are time dependent. And because the long-term system performance varies across the scenarios, so they are scenario dependent. And after predicting the long-term performance of the supply chain under each scenario, then we can compute the three components of the resilience for each scenario. So here, the first resilience component is the hazard event-induced cumulative loss of functionality. So when we look at the long-term performance of a supply chain system, then we can see this yellow area, then that is the hazard-induced event-induced cumulative loss of functionality. So if the negative performance is induced specifically by some extreme natural hazard, and then we are gonna say that this portion is a hazard event-induced cumulative loss of functionality. And then because the number of the hazard events over the planning horizon is uncertain, so here I, the number of the events over the planning horizon for a given scenario is also a random variable. And if the negative hazard, the negative performance has been induced by some non-hazard events, and then it can be classified the non-hazard induced cumulative loss of functionality and can be calculated by using this equation. And if some positive performance has been induced by some kind of opportunities, and this green area can be calculated by using this equation, and then this is the second resilience component, opportunity-induced cumulative gain of functionality. Then why do we have to just measure the overall resilience of the supply chain by using these three discrete resilience components? The main reason for measuring these three resilience components separately is that we can identify which risk factor contribute the most to the supply chain performance and what to target to improve the supply chain resilience. And finally, these three resilience components can be combined together to calculate the overall resilience index. So here the weighting factors are assigned to each of the resilience components and can be determined based on the decision maker's preference toward each of the resilience component. Then every scenario has its unique long-term performance because of the uncertain events and conditions over the planning horizon. And in turn, this resilience index will be just different for every scenario. Therefore, the final form of the overall resilience of the supply chain is not a single value, but it can be represented by the expected value, the probability density function, or the cumulative distribution function. Now, the proposed multi-component resilience assessment framework is applied to a hypothetical forest residual to sustainable aviation fuel supply chain system. So we applied this proposed framework to this specific sustainable aviation fuel supply chain system because this study has been funded by the Federal Aviation Administration. But as I mentioned, the general framework can be applied to any other types of infrastructure systems like the power grid system, transportation system, or the water distribution system. So this hypothetical system is located in the three states, Washington, Oregon, and Idaho states. And then as shown in this figure, this system has three different types of the nodes, the raw material production node, processor node, and the destination node. And then between the supply chain node, there are some transportation edges. And the forest residual are used as the feedstock for the fuel production and converted into the jet fuel and the road fuel through the GFT conversion processes. And the jet fuel and the road fuel are delivered to the two types of the destination nodes, airport and the road fuel market respectively. And based on its location and characteristics, we identify the 3 key risk factors for the purpose of illustration. So earthquake is considered as a major natural hazard that can induce a sudden reduction in the performance of a supply chain system, and then increased amount of forest harvest will be considered as an opportunity, which can bring about some positive performance. And then the GFT catalyst deactivation will be considered as one of the major non-hazard events causing some slowly decreasing performance over time. And then for the rest of the presentation, I'm going to focus more on the earthquake modeling and the earthquake risk assessment because the rest of the 2 risk factors are supply chain specific. However, the earthquake modeling and the risk assessment can be applied to any other types of the large-scale infrastructure systems subjected to the earthquake events. Okay, so it is a seismic hazard map for the entire United States, and the supply chain nodes are layered on top of the seismic hazard maps. So here, as you can see, within this rectangle, the supply chain systems are located in the Washington, Oregon, and Idaho states. And then here, the colors indicate the level of the seismic risk. So for example, the area with the hottest color will experience damaging shaking the most often, such as the west coast of the United States. And then the area within this rectangle, which is our supply chain system, is located in the moderate to high seismic hazard area as compared to the other parts of the United States, especially the feedstock, processor, and the final destination nodes in the Western Washington and Western Oregon states. And therefore, earthquake event is considered as a major natural hazard in this case study. And to stochastically generate plausible earthquake scenario, we first identify seismic faults. So in this study region, there are 69 fault and fault segments, and then we generated 25 seismic events per each fault using the importance sampling technique. And therefore, total 1,509 earthquake scenarios are included in a small but still representative catalog, the stochastic catalog. So for each earthquake event, a ground motion map can be generated. So the ground motion map is if the earthquake will occur at this specific seismic fault, and then the ground motion shaking intensity will be distributed around that area. And then each of the points in the study region will experience different earthquake ground motion intensity. So here in this case study, we can just specifically relate a specific earthquake event to the specific ground motion map, but actually there should be a lot of different uncertainties in generating this ground motion map. So we cannot just make some deterministic relationship between a specific earthquake event and the specific ground motion map. But for the purpose of simplicity, we just assume that if we know a specific earthquake event, and then we can also know the consequence resulting the ground motion intensity map. So the impact of each earthquake event on supply chain performance is modeled by using the probabilistic approach. So first, we need to simulate the number and time of earthquake event for each of the scenario, and then randomly sample earthquake event from the stochastic catalog. So as explained in the previous slide, the location, magnitude, and the spatial distribution of the ground shaking intensities will be known by selecting a specific earthquake event. So for example, if I would like to estimate some structure that the structural damages to the GFT facility located at this specific location, And then I have to find out what will be the realized ground motion intensity at this location of the GFT facility. So this will be the hazard intensity realized at the GFT facility. And then this is the hazard intensity that the GFT facility will actually experience. And then the seismic fragility curve is introduced in assessing the structural damages to each node and link in the supply chain system. So fragility curve represents the vulnerability of the facility and the transportation link. And as I mentioned at the beginning of this presentation, each supply chain node and link will have its own fragility curve because of the different structural characteristics. And then here, the x-axis indicates the peak ground acceleration, which is the hazard intensity. So in the case of the earthquake events, we can consider maybe the peak ground acceleration as shown in this figure, or the spectral acceleration. And if our major hazard is the tornado, and then this x-axis should be the wind speed, which is the major hazard intensity measure. And then if we consider the flooding hazard, and this x-axis should be the flooding height. But the y-axis shows the exceedance probability of a certain damage state. So in this specific fragility curve, we consider the 4 different damage states: slight, moderate, extensive, and complete damage state. And in my previous example, if we identify the ground motion shaking intensity at a specific GFT facility, and then this will be the input for the fragility curve. So let's say that this GFT facility will experience 1.0 peak ground acceleration given a specific earthquake event, and then there might be almost like 30% probability that this GFT facility will experience some complete damage state, and there might be around 80% probability that this GFT facility will experience at least moderate damage state. So that is how we can utilize the fragility curve. And then the consequent capacity reduction due to the earthquake-reduced structural damage can be calculated by using the simple relationship between the original capacity and the new capacity. So after determining the damage state of the GFT facility from the previous step, then we can estimate the capacity reduction from this table adopted from the FEMA HEJU's technical manual. So for example, let's say that by using the Monte Carlo simulation, we just estimated that the structural damages that the GFT facility will experience might be extensive. Then we can utilize either the best estimate damage ratio or the range of the damage ratio. So if you're going to use this one, and then we can just make an assumption that there might be some deterministic relationship between the damage state and the damage ratio. So we can just plug this damage ratio value into this equation to see what might be the new capacity of this GFT facility. And then if we want to just consider some uncertainty within the relationship between the damage state and the damage ratio, and then we can use some probabilistic relationship between the extensive damage state and the range of the damage ratio, as shown in the very right column of this table. And by repeating this process for all the other nodes in the supply chain system, then we can determine the impact of earthquake on all nodes in the system. And similarly, we can assess the earthquake impact on transportation link. So here we made an assumption that bridge is one of the most critical, but at the same time, the most vulnerable components in the transportation system. And for each transportation link, the number and location of bridges should be found. And as mentioned earlier, each breach has its own fragility curve, and its damage state can be estimated through the Monte Carlo simulation by combining its own fragility curve with the seismic hazard map. However, we still need to relate the breach functionality to the link functionality. So here we are using this empirical relationship between the breach damage index and link damage index. So if we find out the breach damage index for all the breaches located in the same link, and then by using this empirical equation, we can find out the link damage index. And then again, we need to repeat this procedure for all the breaches and all the links in the supply chain system, and then input the reduced capacity of nodes and links into the supply chain optimization to recalculate the supply chain system performance immediately following an earthquake event, which means that all of this procedure can generate only one single point immediately following this earthquake event. And then if we want to just to draw this kind of post-disaster restoration the post-disaster restoration curve, and then we can just repeat this procedure. So after just repairing some of the breaches and facilities, and then we can just update their capacities and plug the updated capacities into the supply chain optimization to assess the supply chain performance. Then there will be another single point on the post-disaster restoration curve. So I will just skip the explanation about this opportunity and the non-hazard events causing the cumulative loss of functionality, because as I mentioned, both of them are two supply chain specific risk factors. And by combining these three risk factors, then we generated a set of plausible supply chain performance scenario. So each of the light gray line indicates one possible scenario. And then now let's just focus on only one sample scenario, which is the blue line. And as mentioned earlier, the unmet demand ratio is primarily used to distinguish between the three different resilience components. And if no risk factors occur over the entire planning horizon, and then this UDR will be just a zero and constant over time. So this is the baseline scenario, and by comparing this baseline scenario with the sample scenario, we can identify the time block that can be applied to the first, second, and the third resilience components. And the final output of this analysis is the distribution of the resilience indices calculated for all scenarios. So as mentioned earlier, the weighting factors assigned to each resilience component can be determined based on the decision maker's preference. So we perform the sensitivity analysis of the resilience index to the weighting factors, and then it is shown in the left figure. So it shows the cumulative distribution function of the resilience indices when they are subjected to the two different sets of the weighting factors. So the red curve indicates the CDF of the resilience index when the equal weighting factors are assigned to all the resilience components. And in this case, the earthquake impact on the overall resilience index is considered insignificant because of its relatively short duration and low probability of occurrence. And to avoid such underestimation of earthquake-induced impact on supply chain performance, we propose different weighting factors to different resilience components. So this weighting factor is proportional to the consequence of each risk factor for a given unit time. So by doing so, we can consider both the frequency, magnitude, duration of each of the risk factor. Then let's compare only the median values of the CDF of the resilience index for these two cases. So as you can see from this figure, here the median values of the resilience index when the equal weighting factor is applied is much less than the case when the different weighting factor were assigned to each of the risk factor. This indicates that a decision maker can place a greater importance on the low probability, high consequence risk factors by using the weighting factors shown in this equation. So we can see that the final output of the overall resilience indicator could be really sensitive to the weighting factors. And then now, if none of the risk factors are considered, then the resilience index will be just 0, as shown in this black line. And then there will be no uncertainty because the only reason that there are some uncertainty in the resilience index is because of the uncertainty coming from the risk factors. So here the red curve shows the CDFO resilience index without earthquake events, while the blue curve shows the CDFO resilience index with earthquake events. Therefore, the difference between the blue and red curve shows the contribution of the earthquake to the overall resilience index, while the difference between the red curve and the black curve shows the contribution of the other two risk factors to the overall resilience index. So the contribution of these two other risk factors are pretty significant. And then we can conclude that many different types of the uncertain risk factors should be considered in the resilience calculation, as contrary to the conventional approaches to assessing the resilience of the supply chain system or other types of the infrastructure systems. So in conclusion, this study proposes a quantitative multi-component resilience assessment framework for a supply chain system that considers multiple events and conditions occurring over the planning horizon. And then we just provided more reliable estimates of the system functionality under a wide range of the plausible future scenarios by considering multiple conditions and uncertain events that can occur over the planning horizon. So the case study results can provide some guidance on how to determine the key factors affecting the supply chain resilience. And then it can also give us some guidance about how to effectively combine various resilience enhancing strategies in the maintenance and operation stages. Okay, so thank you for your attention. And then please ask me a question if you have any.
Thank you, June, for the excellent presentation. We have a couple of questions in chat. I will read it to you. So
Yeah,
the first
sure.
one is, resiliency quantification as stated, how does it take into account severity of the disruption? For instance, large functional loss for a minor disturbance versus same loss of function for a more severe disturbance. Should we not quantify the former to be less resilient?
So you mean the severity of the
disruption?
Disruption. So I'm not sure whether I still am sharing my slide here. So can you see my slide?
Yes, we can.
Okay. So here the severity of the severity of the disruptive events can be explained by the magnitude of the lost functionality. So actually the magnitude of the lost functionality can be determined by the combination of the severity of the disruptive event as well as the vulnerability of the system. But if the severity of the disruptive event becomes greater, and of course the loss of functionality magnitude will becomes greater. So this can be just explained by the loss of functionality, and then it can be considered as part of the resilience loss.
Okay, sounds good. Any follow-up question from Mani, do you have any follow-up question? Okay, so the other one, June, we have is for risk assessment and quantification. So the question is the risk quantified over the entire region of the PDF that you showed? How is the resistance defined?
So could you please repeat the question? I'm also looking at the chat, and then it seems that maybe it was the question asked at 11:18 a.m., right? For the
Yeah,
risk
so
assessment quantification.
yes, it's in the beginning. So when you are talking about the probability density function, the question was that is it computed over the entire region of the PDF, or how you are quantifying the risk specifically from the PDF?
So what do you mean by the resistance here? So the resistance of the system?
It's on slide 8. If you go to slide 8.
Slide 8. Yeah.
Yeah, actually, I'll turn my mic on. So it's
Uh-huh.
actually before this slide.
Oh, yeah, the slide number 7.
Yeah, sorry about that. So the last one, you define the risk assessment. How do you quantify the risk here? Did you like calculate based on the entire PDF region, and also the resistance that you have written?
Oh,
How
yeah.
is it
So
calculated?
here, so here the resistance is the building capacity or the building resistance. So if the external factor is applied to the building, and then how much structural loading this building can withstand, that is the resistance. So normally, in order to study the resilience of the building or some kind of the physical facility, and then we have to perform some finite element analysis and nonlinear dynamic structure analysis to see how this building behave when a specific structural load is given. So in order to determine the resistance, actually the structural load should be the input, and then we can just find out some corresponding resistance, because the resistance is the building capacity when a specific structural load is given. So it will require some structural engineering knowledge to study the resistance part of the system.
Yeah, sure. Thanks.
No worries.
Great. Thanks, June. Those were the only questions I have in chat. We have a couple of minutes, so if anyone has any questions, they can unmute yourself and ask. So if not, let me ask a closing question. So June, what are your thoughts on applying this approach? How it will be different or similar when you are looking into some sort of systems that also have got the physics going on, for example, power systems infrastructure that we are seeing, or water networks that we are seeing. How does this analysis, in your opinion, changes, and what we should be careful about when we are conducting similar analysis for extreme weather event kind of scenarios?
Okay, so I think the major differences between some different types of the infrastructure system can be the systems modeling. So in the case of the supply chain system, we just utilize our own performance measures and optimization procedure. So here, our performance measure is the unmet demand ratio, which is the performance measure to see how this system can meet the customer demand at the final destination node. But this kind of the performance measure can be different for every different types of the infrastructure system. And then accordingly, the systems modeling should also be different. So for example, in this case, we are specifically using some supply chain optimization software program to see what will be the impact of the earthquake event on the supply chain performance. But in the case of the power grid system, I believe that you guys also have your own software program to see how this system will respond to some kind of the external forces or some internal uncertain events and conditions. So I think the major difference between the different types of the infrastructure system should be the performance measure and the systems modeling, but the basic procedure could be just the same.
Great, sounds good. Thank you so much, June, for your presentation today. We greatly enjoyed the talk and the topic, and it's very relevant as we are, we are seeing more and more of these scenarios due to climate change. So thank you again for speaking with us today. And with that, I will adjourn our ESIC seminar meeting for today. Have a great day, everyone. Thank you.
Okay, thank you. Bye.
Thank you.